Hey folks, welcome back. In this video we're going to go over question 3 from the 2016 SQA Advanced Higher Physics exam paper, so let's get into it. Question 3 says a spacecraft is orbiting a comet as shown in figure 3. The comet can be considered as a sphere with a radius of 2.1 times 10 to the 3 meters and a mass of 9.5 times 10 to the 12 kilograms. So there's the comet and there's the spacecraft orbiting. Part A says a lander was released by the spacecraft to land on the surface of the comet. After impact with the comet, the lander bounced back from the surface with an initial upward vertical velocity of 0.38 meters per second. By calculating the escape velocity of the comet, show that the lander returned to the surface for a second time. And you'll see there's 4 marks available here. Well, what we need to do here is calculate the escape velocity for the comet and then compare this with the velocity of the lander. So writing down what we know from the question, we're trying to find the escape velocity v escape. We know the universal constant of gravitation, capital G, from the datasheet is 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared. We know that the mass of the comet M is 9.5 times 10 to the 12 kilograms from the question. And we're also told the radius of the comet in the question 2.1 times 10 to the 3 meters. So writing down our equation for escape velocity, we have v escape equals root 2 gm over r. Substituting in the numbers gives the square root of 2 times 6.67 times 10 to the minus 11 times 9.5 times 10 to the 12 divided by 2.1 times 10 to the 3, and if you put all of that into your calculator you should get an answer of 0.78 meters per second. And remember we said we're going to compare this velocity with the velocity of the lander. So we can say therefore, since the velocity of the lander is less than the escape velocity for the comet, the lander will return to the surface, i.e. it will not escape the comet's gravitational pull. In other words, the lander would need to have a velocity greater than 0.78 meters per second in order to escape the comet's gravitational pull. B part 1 says to show that the gravitational field strength at the surface of the comet is 1.4 times 10 to the minus 4 newtons per kilogram. And you'll see there's 3 marks available here. Well, we can start by saying that the gravitational force of attraction between a mass little m and the comet of mass capital M can be represented by both F equals mg and F equals gmm over r squared. So these are our 2 gravitational force equations, and equating the 2 will give us mg equals gmm over r squared. Now cancelling the lowercase m's from both sides gives us g equals gm over r squared. And now we've got a relationship for gravitational field strength in terms of the universal constant of gravitation, the mass of the comet and the radius of the comet. So substituting in our numbers, we have 6.67 times 10 to the minus 11 times 9.5 times 10 to the 12 divided by 2.1 times 10 to the 3 squared. And putting that into your calculator should give you an answer of 1.4 times 10 to the minus 4 newtons per kilogram. Lastly, part 2 says using the data from the space mission, a student tries to calculate the maximum height reached by the lander after its first bounce. The student's working is shown below. So they started with one of the linear equations of motion from higher physics, v squared equals u squared plus 2as. They then substituted in some numbers to get 0 equals 0.38 squared plus 2 times minus 1.4 times 10 to the minus 4 times s, and then rearranging for s they got an answer of 515.7 meters. It then says the actual maximum height reached by the lander was not as calculated by the student. State whether the actual maximum height reached would be greater or smaller than calculated by the student. You must justify your answer, and you'll see there's 3 marks available here. Well, we can say that since the gravitational field strength g and therefore acceleration due to gravity a decreases with height above the comet's surface, the acceleration a will reduce with height. And remember that's because acceleration due to gravity and gravitational field strength are equivalent. So the further away you get from the comet's surface, the acceleration decreases. And therefore we can say the actual maximum height reached by the lander, which is s, will be greater. And the way to see that is to look at the working here. So if you're rearranging for s here, you can take this term over to the other side, and then you're dividing by 2 times a. So to get s on its own, you're dividing both sides by a smaller a value, and that will give you a larger s value. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.